If it's running out of battery, we have the backup.
Okay, I'll turn.
Many cavities or many modes for simulation, computation, sensing, etc. Kick us off is Ella from Stanford talking about multimode cavities for spin glasses and associative memory.
Okay, thank you very much. Is this too loud? I always feel like I'm too loud. No, it's good. All right. Okay, so today I'm going to tell you about making quantum optical spin glasses, and I'm going to spend a little bit more time than I usually do talking about the cavities because this is a crazy cavity workshop. So I'm not sure if I'm going to have time to talk about the associative memory, but I will do my best to get there. I see that we're starting a little bit late, so we'll just push it a little bit later. Okay, so the people who've done all the hard work are listed here. A lot of these projects were led by Brendan Marsh and Ronan Croze. They're both postdocs elsewhere. Dr. Yumpang Ji is now also in Boulder here. And then we have some wonderful new students and medium new students, or maybe older students. David Atry-Schuler, Devin Bowman, and Julia Sokolov. They're in the audience. They are the people who actually know everything, so you should talk to them. We have really wonderful theory collaborators that we've worked with over the years. Srenko Paul-Christian at Princeton, Jonathan Keeling at St. Andrews, and our local Surya Ganguly. And we have two other experiments that we can tell you about, and you can tour our labs this afternoon. Okay, so let's begin. This thing's making me nervous, so I'm going to go over here. Yeah, great. All right, so what are spin glasses? Spin glasses are frustrated, disordered magnets. So colloquially speaking, they are magnets for which the spins are frozen in random directions. So your immediate impression of that might be, oh, they're just random. They're kind of like a frozen paramagnet, but they're actually not. Like the frozenness about them is actually quite structured. Like the random spins are maybe random in a snapshot. There's actually a lot of structure and interesting physics to explore there. They're not super exotic. You can find them in copper if you dope it with a magnet, like manganese, and you know, they're there. You can tell that they exist by putting them in a magnet and seeing their susceptibility. You can't look at the spins, you know, each like 10 to the 23 spin and figure well what's going on. But we know from bulk measurements they exist. They also exist in more exotic materials, like Cooper superconductors. So we don't talk about this very much, but at low temperatures, there's a spin glass phase. They show up like all over the places, like the surfaces of superconducting circuits and so forth. They're around. And basically, anytime there's magnetism disorder, you'll probably have a spin glass lurking somewhere. All right, so what's a defining characteristic? Well, one perhaps defining characteristic is its free energy landscape being very, very rugged. So this is a very poor caricature of that free energy landscape. This is in one dimension. It actually lives in an n-dimensional space, so you have to use your imagination to think about what that might look like. But if you kind of order the spin configurations intelligently, generally speaking, in this high dimensional space, you have like alpine peaks with very, very deep valleys. And say if you're a skier at the top, you know, and you get landed by a helicopter in the same spot each time, sometimes the wind will buffet you down into one village, and sometimes it'll buffet you down to another village. But either way, you get stuck in that village. And so just like in the Alps, where people, you know, develop their own cheese and wine and dialect, and you know how this is, right, Dylan? You know, you can never get out. So even if you might be close by, you're kind of stuck there. And this is the notion of the breakdown of ergodicity. So spin glasses are no longer ergodic systems at low temperatures. This is the whole world to that system over here. That kind of weird physics can be described very, very simply, it turns out, by something called the Edwards-Anderson Hamiltonian. And it just looks like an Ising Hamiltonian, and it is, except for this JIJ coupling is now randomly signed. So if we represent this as an all-to-all network, so like take an approximation of this or a limit of this where every spin is coupled to everyone else, and you randomly assign a blue linkage if it's positive, ferromagnetic, or orange if it's negative, and anti-ferromagnetic, then this becomes a type of spin glass. This one's called the Sherrington-Kirkpatrick spin glass. So it turns out that, like, generally speaking, this is unsolvable. Like, no one has like figured out the structure, the order of the ground states or the low energy configurations of the system. This approximation to that, you know, where everything is coupled to everything else, has been solved. It's a very famous solution. In fact, it's a solution that won Giorgio Parisi the Nobel Prize in 2021. His solution, and I'll motivate this later on, is called replica symmetry breaking. It's one of the few spin glasses that has been rigorously figured out. But more generally, like, you know, short range spin glasses, you know, where maybe only the nearest neighbors are linked, nobody has the answer for what the order of that spin glass is. It's one of the greatest unsolved mysteries in all of statistical mechanics. And because, as I'll show in a moment, it relates to all sorts of, you know, NP complete problems, it's one of the greatest you know, unsolved mysteries in all of physics, I think. Okay, so you know, to make that point a little bit better, you know, spin glasses, because of this property that mathematically they're mappable on all sorts of problems, they serve as models for complex systems more generally. Okay, so complex systems is kind of a nebulous category. You see it, you know it when you see it. And spin glasses are kind of a system for which there's a mathematical structure that you can start to investigate them. So, you know, of course, this is a very popular thing going on right now with neural networks. And you can see, like, you know, recurrent neural networks have, you know, pretty much exactly the same structure as a spin glass, and they basically are spin glasses. And this physics underpins a lot of what's motivating, you know, all of the energy going on here in Silicon Valley. So it was particularly exciting that last year, John Hoffield won the Nobel Prize. What did he win the Nobel Prize for? He won the Nobel Prize for exactly this model, the Sherrington-Kirkpatrick model, figuring out that if you structure this GIJ matrix in a learning kind of way that's like natural to what, you know, humans do in terms of learning in what's called a Hebbian sense, then you can construct a useful neural network called an associative memory. And so this sort of construction, you know, garnered the Nobel Prize because it mapped, you know, connected some very profound statistical mechanics model of spin glasses to some biological functionality, associative memory, and to computer science notions. And so that was a very profound and deep thing. We've been exploring this, and if I have time, I'll get to it, and how to make this out of atoms and photons. Okay, so this is, you know, I think this physics is so much fun that, you know, more than a dozen years ago now, we set the ship of my group sailing towards this destination of actually creating a spin glass using atoms and photons in this quantum optical context. And so it's taken a long, long time to do this. We had to develop many techniques, but now I'm going to tell you kind of, you know, our first results on this. So the system that we've been studying kind of has this cartoon. You have at the center, so it's a Fabry-Perot cavity here, but a very special kind. Well, actually not very special, but it's an unusual kind, at least nowadays. And in the center, we have atoms. They're actually not individual atoms. They're clumps of atoms that are controlled by, their positions are trapped and controlled by a two-dimensional tweezer array. So think about this in 2 dimensions. It's just a cartoon here in 1 dimension. Each one of these is a little BEC. So we start with a big BEC, and then we tweezer it apart into up to 25 little baby BECs coming out from that. Each one has, let's say 10 to the 4 atoms per site or so. And then we plug the whole thing in. It's a non-equilibrium system. We plug it in by driving it with a laser, a coherent laser from the side. So light comes from the side, scatters off of each of these BCs into the cavity. And what you'll see is that this looks really weird. Like this is not your grandfather's cavity. This is a very different kind of mode structure. Instead of one big Gaussian mode that they all scatter into with some because they're in different spots, some different coupling. Here, they scatter into their own kind of bespoke mode that we call a super mode. And so this clump of atoms will scatter into this mode. This clump will scatter in this mode. Each one of these we call a super mode, because what else would you call it? And these super modes can resonate back and forth and then mix with these other super modes, which I'll explain later on, to give you interactions between all of these. So before I explain that, I'll just say that the light can leak out of the cavity and be holographically imaged on a camera, and that can provide local images of the atoms and actually the spin state of the atoms at the plane inside the cavity. So what's unique about this or interesting is that you get spatial information because this sort of acts like a lens system now. Like it gives you resolving capability, even though it's a cavity. So you can actually, in this plane here, in the object plane that you map out here, you can actually see like, okay, this clump of atoms was spin down, and this clump of atoms is spin up by taking the phase measurement from the holography. So we've done this up to networks of 25. We can extend this in the future, we believe. But this is a n equals 20, it's n equals 25, et cetera. Okay. So then the weights and the connections for this JIJs come from how these beams, these supermodes mix with each other. I'll get to that later. You can program the system from the input side over here with a digital mirror device or SLM, whatever you like, with phase sensitivity coupled directly into a supermode that say targets this clump of atoms or that clump of atoms to give you a longitudinal bias field to program the system. Okay, so just so that we're clear, this is not a spin, quantum spin 1/2 system yet. We think it's possible using Rydberg blockade. We've mentioned this in some paper here, and we're going to write a new paper about that eventually. But right now, these are collective spin states. So, the cavity is very quantum mechanical. It's like in a vacuum state initially. The atoms go through a very transiently entangled state, but the entanglement probably at this level of this many spins doesn't really matter that much. Okay, so this is because it's a cavity, crazy cavity meeting, I throw this slide up. So this is what the thing actually looks like. We've had this machine operating for about 10 years now. There's a cavity inside a BEC machine. What's different about this is that the upper mirror can be moved up and down with the slipstick piezo. And that can give us whatever a ratio of radius of curvature to mirror length we like. And so sometimes we want the length to exactly equal the radius of curvature. That gives us multimode cavity. And we can do that, or we can go to other lengths as we like. It's single atom, strong cooperativity. And we actually have a new machine with dysprosium now, with everything upgraded and slightly better parameters and so forth. So that's what that looks like. But everything here I'm going to talk about has to do with rubidium. All right, so let me, again, because it's a crazy cavity workshop, let me belabor the point of what a multimode cavity does. So normally when you have a cavity that you just have 2 mirrors, you put them at some length that you don't really care about, you just put those mirrors away from each other. You just resonate at a single mode at a time. Each one of these has a unique frequency. But there are certain ratios of the radius of curvature of the mirror and the length that gives you a degeneracy where some of these or most of these oscillate at the same frequency. So for a confocal cavity where the length is equal to the radius of curvature, that's a cartoon of a confocal cavity, has these hourglass-like modes. And to like visually see that it's degenerate, you could imagine that this black hourglass trace has the same path length as this gray one, because the gray one extends a little bit further into the mirror curvature. You have to like sit there in a dark room and think about it, but it actually has the same path length. So if you do this experimentally, if they're not actually, L is equal to R, then you can see all of the resolved modes and their ducklings and so forth. But if you bring them close together, then they collapse into one resonance. The resonance is not a perfect delta function because of aberrations. And gosh, Ramin, we love to fix this issue. This is the thing that we'd like to improve on. So in order to make this sort of look, like a delta function, you can pump the system off resonantly. And then from that distance away, this bandwidth here looks more narrow and like a delta function. So this has somewhere like 1,000 modes inside of it. So you can ask yourself, what does this buy you? Well, I gave you a hint earlier. It allows you to have these little spots, but where does that come from? It comes from the fact that you can now transform into a different basis of thinking about your cavity modes. So instead of thinking about your cavity modes as these non-local functions that just kind of spread everywhere, Hermite-Gaussian polynomials, you can take superpositions of these, some together, some hundreds or thousands of them. And when you do that at each spot within the transverse cavity, you get a localized little dot, okay? If you have an infinite sum, you get delta functions. And you can just tile in a spatially localized way a new basis set that's localized, that's just like, say, a square lattice array of little dots. Now, in practice, you don't have a complete sum, so it has some width. But without too much work, well, a lot of work, but without too much effort on the design of the mirrors, you can decrease the width of the spot from the Gaussian waist of, say, 35 microns for a centimeter long cavity to something that's sub 2 microns, okay? Yeah.
This is like we learned this story in degenerate case in quantum mechanics.
Yeah.
So I understand you're free to pick a new bunch of eigenmodes.
Yeah.
But just because you pick them doesn't mean the cavity knows that you picked them.
Yeah, that's right.
To make this particular
So
spiky guy special.
when you put a dipole in the cavity, that dipole will preferentially couple to the modes that have a coherent superposition at its location. And that's why in the previous slide, you saw that each clump of atoms had its own tight spot around it.
So until you put the atoms in there, those aren't
No,
in any way special.
It doesn't matter. You could have Lugger Gaussian if you wanted to, right? So okay. So anyways, going back to the story, the point is that you shrink the electric field and you increase its intensity at the spot where you have your dipoles. And this is what we call a local supermode. So what's cool about this is that you greatly increase the electric field at the position of the atoms, and you greatly increase the effective numerical aperture of those mirrors, because now you can resolve things at this level, not at this Gaussian level. Okay, so in an idealized degenerate cavity where all of these were exactly on top of each other with a width that equal to kappa, their line width, then you would enhance cooperativity by exactly this ratio. And so a caution is that we're not perfectly degenerate here. So there's some spread here. So we have to operate, or we like to operate off resonance. So here, there's kind of a funky notion of cooperativity. It's not exactly the same, it doesn't serve the same function as cooperativity, but you still use this enhancement ratio of about 20 as something that you can understand as an enhancement of the dispersive photon-mediated interaction enhancement. So your photon-mediated interactions are enhanced by this factor of 20, or you can think about the resolution of the cavity is enhanced by a factor of 20. And this is the thing that multimode cavities really buy you at this level. Okay, and I'll come back to this point in a moment I'm going to go take a little bit of a deeper dive. So we use two different types of multimode cavities, and there's an infinite series of these things. But the simple ones we use are the confocal cavity, which has this hourglass-like shape. If you take a normal cavity with the families of modes like this, and then you bring L is equal to R, then you reshuffle these higher order modes into families that occur at every half free spectral range. So the even modes stay here, the odd modes go here, and then they alternate, and they also alternate in the longitudinal pattern as well. There's other types of multimode cavities, and we'll use this for most of the rest of my talk. These are called, we call these M over N cavities. It's some taxonomy that we've developed. This number here tells us how many foci there are in the cavity, roughly speaking. That's the M. The 7 is how many times the free spectral range is divided by subfamilies of how they rearrange themselves. So this has 7 subfamilies. And so this is the electric field. This is a confocal cavity electric field. What you see, what's interesting is that you have this tight spot, which is that supermode I was telling you about, but it has to go back and forth twice. That's this 2, in order 2 round trips. And so what happens when it hits the mirror is that it comes back as a large Fourier transform of spot. Fourier transform of spot is a cosine. So you get this kind of cosine undulating field before it reforms in this virtual image over here. The 4/7 cavity is far more complicated, but you can see there's 1, 2, 3, and then there's a half here and a half here. 4 spots, that's this 4 here, and you kind of see what that is. And you have this non-local undulating field and then the tight field over there. Why do we do that? Well, I'll get to that in a moment. I'll tell you what each one does in terms of spin physics. So let me tell you what the spin is, though, before I do that. So the spin is something we learned from Tillman and others how to make a spin out of a BC. You take a ground state BC in a trap, and let's just call this on a Bloch sphere. Collect the Bloch sphere is the -z point. When you pump the system hard enough, transversely, turn on your pump hard enough, the system will undergo a super-radiant-Dickey phase transition. Never mind exactly what this is. The effect of it is that this BEC forms a checkerboard density wave pattern. And so in our nomenclature here, you get 2 different checkerboard patterns, like don't stress out trying to see that they're different. But one you can call the -x point on the Bloch sphere, and the other one is the +x. And so this forms an effective Ising spin. You go from -z to plus or minus x, like so. And there's another way of doing it where you have a continuous distortion here with a complex superposition. You can get an xy one as well. So that's our spin that we will couple. Why do we use a BC? It's not because it's of the coherence. It's just near k = 0, and it's nice to use. So now let me put everything together and tell you how we get the photon-mediated interactions. So if we use a confocal cavity and say you put some clump of atoms here, they form that preferred supermode at that position Ri. The light comes back after we pump the system, and we'll hit another clump of atoms at position Rj. And that mediates through a virtual interaction, the Jij interaction, like so. And if you adiabatically eliminate the atomic excited state and you adiabatically eliminate the photon field, then in this dispersive limit, what you get is a transverse spin model that looks like this. So you have the transverse field, which is proportional physically to the recoil energy of the atom, because you're forming this density wave, and that sets like the spin gap. And then the interaction has a strength here that's on the order of about 1 kilohertz. And that's really great. It's like much greater than contact interactions. It's amplified by the intensity of the light coming in. This is the single atom coupling strength, and then 1 over delta. Delta A is the atomic detuning, delta C is the cavity detuning. So this tells us our coupling strength. And then this is the shape, the structure of that interaction. It turns out for a confocal cavity, because of the sine and the cosine longitudinal fields that are in each one of those families of degenerate or near degenerate modes, you get something that looks like XX minus YY. That's very strange. That's a strange XY model. It is what it is. It's kind of cool. We've explored this. But the essential point is that never mind what this thing is, the structure of the Jij gives you something very, very interesting and unique. All right, because of this fact that you get the Fourier transform coming back and you get this undulating, like cosine-like field that changes sign, the interaction between 2 spins at position R and Rj is the dot product inside of a cosine. So if you just move these slightly with respect to the waist of the cavity, then you'll change the sign. If you do that randomly, you'll get a random signed interaction. And this is how you get that spin glass. This is an all-to-all Sherrington-Kirkpatrick-like spin glass interaction. And so that's the secret to how we do this. It's not something that you generically see in a condensed matter textbook. This is a weird interaction form that you get from this optical system. So, it's fun playing with XY models and XX minus YY models. And we did that in this recent science paper. But what's really more enjoyable, generally speaking, is to use Ising interactions. And that's why we go to this weird 4/7 cavity. And it turns out that if you work out what this is, and you do this through Green's function type formalism, you just get a much simpler interaction that is just literally like an Ising. Everything else is the same, but it's an Ising interaction. So that's what I'll use for the rest of the talk, is this type of interaction. Okay, so going back to the spin glass story, how do you know that you've created this very weird state of matter? Okay, so what's the microscopic fingerprint? All right, so let's contemplate doing an experiment where you put the atoms in some location, some Ri's and Rj's, that realizes a random Jij matrix, okay? And you do that the same each time. You recreate the BEC, you put them in the same locations, but just like the wind buffeting the skier going to different valleys, thermal fluctuations, quantum fluctuations will buffet the organization of the spin configurations into different minima, okay? And you want to catalog all those minima. So the positions realize some high dimensional landscape. You run the system each time, starting from like the same mountaintop, and sometimes it goes into this minima, and sometimes it goes into that minima. And you collect all of the spin configurations, alpha and beta. You collect like hundreds of these things, and then you make some comparison. All right, so what's the comparison? It's what's called a spin glass order parameter, or the replica overlap. The magnetization is not good enough because a paramagnet and a spin glass both have 0 magnetization. So you need something else. So you take this 2-spin kind of correlator. It has the structure of the following. You take the spin for replica beta of spin site I, and you time average it. And you do that same thing for spin alpha at that same site I. And then you multiply them together, normalize. And you ask, is it 0? It might, if it's 0, it's just trivially 0 because you time average a paramagnet is just fluctuating too much. And so that's 0. If it's always plus or minus 1, then you have a ferromagnet. And that will happen if like all the spins, every time you do it, are either always up or they're always down. So if they're both the same, then that's plus 1. If one replica alpha is plus and the other one is minus, then they're always going to be minus 1. So you get plus or minus 1 for a ferromagnet. But if you get values between 0 and plus or minus 1, that indicates spin glass order, because what it's saying is that there are some strings of those spin configurations that are similar in this valley, in that valley. It's like, okay, they're both sort of speaking German, but there's very different dialects, okay? So that correlation is somewhere between 0 and plus or minus 1. And that, combined with 0 magnetization, is the smoking gun for a spin glass. Okay, so that's what we learned from Parisi in the 1980s. It's not the only thing that we need to do. There's also something called his order parameter. Let me motivate what that is. Okay, so the spin glass order parameter for just one realization of the disorder, meaning the Jij. I put the atoms in one position, and I put them in the same position each time. That realizes one particular Jij matrix, one particular landscape, one particular, and then I can go in and I can measure different copies or replicas of the system by running it over and over again each time. If I take that overlap distribution, I will get some correlator like this, okay? So these peaks here are the plus or minus ones. You call them the goalposts. He was a soccer fan or football fan. And those are the plus or minus ones. They're a little bit broadened because the simulation we did is finite size and has a little temperature to it. But then you see these peaks in the middle between those. Those are the partial peaks due to overlaps between replicas. So this is a spin glass order parameter. But if I do it again with moving the atoms in slightly different positions to realize a different disorder, I'll have a completely different landscape, and that'll induce a completely different distribution of those peaks. That's okay. That's exactly what he predicted. He predicted that from disorder realization to disorder realization, you'll have, in the thermodynamic limit, delta function sparse peaks that will change in a random way from realization to realization. That's not a great order parameter in the thermodynamic sense because it depends microscopically on disorder, the realization of quench disorder. So what you do is you take an average over all of this, and when you do that, you get the net between the soccer goalposts. To me, that looks like a football goalpost, like gridiron football, but okay, I'm an American. So that's the each one of these is a smoking gun for a spin glass, but this is the correct thing that you would use for a thermodynamic order parameter. Okay, and just to compare, in our simulations, this is what the disorder average would look like. This is the ferromagnet, that's a paramagnet, okay? So let's see if we can do this in the experiment. So most of our experiments have not been done with n equals 25 network. It's just too time intensive to explore completely all of the spin configurations that you get from that in a fair sampling. It's just, we've already made an experiment that's too big for us to do that. So we limited ourselves to n equals 16. It's more robust, and you can exhaustively explore it without exhausting your graduate students, which is an important thing not to do. So what we do with the n equals 16, these are some example experimental images. We do like 400 or 800 replicas. A replica is just a running of the system with different noise disorders, noise realizations, okay? But the same quench disorder for all of these, so the same atomic positions. And the camera averages, so we take each one of these images as being this expectation. And then you after the fact, you make these overlaps, okay? And if you do it for this set of data, we get this for this icing spin glass. And this really is exactly that smoking gun of a spin glass. You have the goalposts, and then you have the sparse peaks in the middle. And they're a little bit broad because of finite size and whatever, but that's exactly what you would expect. And then we change the positions just by a few microns. So each one of these is about 5 microns wide or so radius. We move them over by about a radius or two. That realizes a completely random cosine R1.R2, like a completely different Jij realization. And we get a completely different looking overlap for each one. So each one of these is a different realization of that spin glass. And then you can average them all together and you get something like this. And you average more and more, it just fills out and gets smoother and smoother. And so that combined with the fact that the magnetization is around 0, this convinces us that we have a spin glass. So we contend that this is the first direct observation of replica symmetry breaking, that famous thing from Parisi, which just says that like the replicas that you make have no obvious symmetry between them. It's not like just like flipping a Z2 all up, all down. There's some slight correlation between the dialects of these different villages. There's slight correlation between the spin configurations in each one of these minima. That's replica symmetry breaking, RSB. And that has never actually been seen at the experimentally at this single spin level. It's been inferred in very abstract ways from like random lasers, but mostly it's all just been numerical that people believe this thing exists. But we now directly see it. Actually, this wasn't the first. The first was that XX minus YY model from the confocal cavity. That gives you this cool looking twister map. It's just a vector map, and we color the spins by the angle along this U1 symmetry. And then you can just form the same kind of plots. They're just two-dimensional plots now. So it's a little bit more complicated. And if you want to know more, you can look at this recent paper. Okay, so that's not all Parisi taught us about this all-to-all connected spin glass. Just like when we talk about normal phase transitions, like going from a liquid to a solid, the symmetry that's broken when you do that is translational symmetry. You form a crystalline lattice. The structure that emerges is that lattice, the thing that has that periodic structure. So with the spin glass in this, this completely connected model, the symmetry that's broken is replica symmetry. But what is the structure that emerges from that? And so the structure is something called ultrametric structure or fractal overlap matrix. So this is a very abstract and weird thing. So let me try to motivate it a little bit. If we take those overlap values, Q alpha beta, and do 1 minus them, we can form some notion of a distance between two different replicas, alpha and beta. And then we can look at 3 pairs of those distances of 3 pairs of points, which are these replicas, and ask, does it satisfy the weak or strong triangle inequality? So our everyday world here satisfies the weak triangle inequality. This is just like kind of intuitive for us. But it turns out that the structure that emerges through this spin glass transition in this Aldal Sherrington-Kirkpatrick model is the strong triangle inequality of relationships. So you either get equilateral or isosceles triangles. And so if you take all of the alphas and betas and try to make a relationship of them in space, you naturally form something that looks like a family tree. Okay, this is how family trees are organized. You know, children, you have to go up to parents or grandparents to get to cousins and so forth. Okay, and if you plot that two-dimensionally, you see the structure finally. It looks like this block diagonal fractal-like matrix. Okay, where no. And so this is the thing. This is the structure that emerges. Now the weird thing is that this is a structure not of a single realization of your experiment, just like cooling the water is, has a crystal mass. That's like a single realization. This is a realization. This is a structure that emerges in a collection of realizations, and that seems weird, but it's totally fine in the structure of statistical mechanics. It's just what you do for systems that don't have self-averaging. Okay. Spin glasses are not self-averaged, they have quench disorder. So the structure that emerges is after you average over quench disorder, okay? All right, so he won the Nobel Prize basically because this type of structure turned out to emerge in all sorts of complex systems. I told you about spin glass and complexity. This is really the connection here, is that this structure emerges all over the place in all sorts of numerics, but has never been seen microscopically from microscopic degrees of freedom. So that's what we've done now. So we now have seen ultrametricity from looking at the intrinsic degrees of freedom of the system. So this is one spin glass realization. So one set of positions of the atoms, another one. So these 4 different examples of quench disorder. These are the overlap matrices, and they look, they're block diagonal looking. They're not as beautiful as this thermodynamic limit, temperature equals 0, calculation from Parisi, but this is what a real system actually does. Now, of course, this is not a family tree that you would actually want for your family, but it's what we've made with our atoms in the laboratory, and so we're proud of it too. Okay, so this is what we contend is the first direct observation of ultrametricity in a physical system from the microscopic degrees of freedom. Okay, so if I have a few more minutes, 5 more minutes, I am going to race through another topic. So you can take that system, and Hopfield told us that you can use this as a Hopfield associative memory. So if you take this Jij matrix and make a special version of it, where you take the sums of outer products of patterns, like pattern of Einstein or Curie or Feynman, then you create your own landscape that's much more regular. And if you start with some disorder, like say you corrupt a pattern or you have missing information or misinformation, then dynamically, if you minimize energy, you'll get back to the original pattern and you'll what's called pattern complete. And this is a very useful thing. It's what we're doing. Like I see Jack today and it's like, oh yeah, that's Jack. He does have the same jacket on, but still, if he had a different jacket on, I would know it's Jack, okay? Because I can pattern complete. All right, so I'm gonna skip this. Basically, if you add too many patterns together, you get a spin glass, and nobody thought a spin glass would function as an associated memory. We thought otherwise in this theory paper from a few years ago, because multimode cavity QED gives you cavity cooling, like Vladen predicted 20 years ago or so, 25 years ago. And it turns out that allows you to use a spin glass as an associative memory. So we repeat the experiment. Now we put the atoms in some location that realizes some landscape. But now we designate each minima as some pattern that is a stored memory pattern. We call these memory patterns now. And then if we program into the system some memory pattern that is close to, say, this one that's stored here, but has some flipped errors. So you see this one, this is the stored memory, has a blue dot here that's up, but now we try to program it with down, and this one is up, and this is down. You're off to the side, it's a higher energy stimulus, but not so much that it's in one of these other minima. Then if we run this system, we expect to get the recalled memory, okay? And not one of these others and make a mistake. So doing that with this memory, we get this recall curve, where as we increase the number of errors that we make and average over all different realizations of errors, we can actually make a perfectly recalled memory up to about 50% we can make a perfectly recalled memory with no errors come in. If we put 1 or 2 or 3, we diminish the recall probability, but it takes 4 spin flips actually to get to 50% recall. That's pretty good. So that means that effectively this is the size of that basin of attraction in this high dimensional space. So you can actually flip a large fraction of the spins and still recall that, oh, this was the pattern. So it's like, you know, there's Randy over there and like he has like a pink wig on. I would still recall him as Randy, right? That's what you normally do. Right? So then we wanted to average over all sorts of realizations of disorder and at different network size to look at scaling. And so we did this with the n equals 16, 12, 8, 4 network. We could go to 20 and 25, takes too long, it's not as robust. So we stay with 16. And the punchline, because I'm running out of time, is that we do much better than the Hopfield model predicts. This is the Hopfield model down here. We do several factors better in terms of the memory capacity defined by this like 50% recall probability. And we can do it for a multitude of different JIJs. They have different basin sizes, so they have different memories, but you average them and they're consistent with this function that you would predict from the SK model, the spin glass model that would eventually, you know, looks like an exponential. We don't have enough data to really claim it's an exponential, but we're definitely doing this experimentally for the first time, much better than the Hopfield model predicts. So, so that kind of confirms this like cavity cooling dynamics that allow us to increase the capacity. But we made a discovery that we didn't expect at all, which is that if you loosen up the tweezer traps to allow the atoms to move, you double the capacity all the way up to about 24 memories from, you know, just 3 that you would expect from the Hopfield model. What the heck is going on? What's going on is that we have discovered a dynamical connectivity. The JIJ matrix depends on the positions, and that's a form of plasticity. So, and I'm racing through this right now, but if you have a tight trap for each one of the atoms, and you look at 2 different memories and where the spins are, they're kind of close together, but not always the same position. If you loosen the trap and allow them more elasticity to move in response to the stimulus, and you get bigger excursions that are memory dependent. And that's what gives us this memory enhancement. And that's, you know, known as short-term plasticity, like how we learn in our minds. We change the synapses in a plastic way to learn. The atoms are doing that naturally. And so if you want, you can consider this a form of a polaron-driven distributive spin glass. So it's a very, very new form of spin glass that is intrinsically trainable because photons can move atoms around. And that's going to be a very, very fun and impactful thing to study going forward. So to summarize, we've directly observed replica symmetry breaking and ultramatricity for the first time at the microscopic level. Other people have predicted other cool things that you can do with spin glasses, and we can explore all these other ideas. We'll explore this plasticity-based learning that we discovered. You can then just go back, you know, 40 years or more and do susceptibility measurements, but now for each spin individually or correlations of spins and ask what that teaches you about aging. And you can push into the spin 1/2 regime. We have a theory paper that shows that you will get entanglement on a millisecond time scale and eventually create short range spin glasses to address this 40-year-old question of what is the order of spin glass. All right, so with that, again, these are all the people that do the real work. We've done other fun things with multimode cavities, like make vibrating supersolids or, you know, optical lattices with sound. We have a new experiment with dysprosium in these multimode cavities, and then previous work with dysprosium focused on 1D gases and scar states. So thank you for your patience.